Continuing on in Unit 5, we're going to talk about strong acids and strong bases, as well as weak acids and weak bases. So strong acids are strong electrolytes. We mentioned this in the previous lecture. So because they're strong electrolytes, that means they ionize completely. So they form exclusively ions, no molecules are present. The strong acids that you should memorize for this course are HCl, HBr, HI, HNO3, H2SO4, and HClO4. So now if I put HCl with an arrow and water over it, you know that it's a strong acid. So it's a strong electrolyte. It ionizes completely. It dissociates completely. Remember that ionize and dissociate mean the same thing. So if you were to measure the conductivity of this solution, it would be a high conductivity because there are only ions present. Another example of a strong acid ionizing, HClO4, perchloric acid. So it breaks up into H plus AQ and ClO4 minus AQ. Now, if you wrote H3O plus instead of H plus, that would be acceptable as well. So either one is acceptable. Make sure you understand that they're strong acids, strong electrolytes. They ionize completely. And it is a good idea to memorize all 6 of these. Now, weak acids, on the other hand, are weak electrolytes. They partially ionize. So, weak acids that you should know, HF and carboxylic acids. Remember that carboxylic acids look like this. And carboxylic acids can be written a variety of ways. We learned about carboxylic acids in Unit 4. We saw them written out completely like this. I'm just going to draw out acetic acid. So acetic acid is a 2-carbon carboxylic acid. So you can see it written like this, or you can see it written C2H3O2H. In both of these cases, the hydrogen that comes off or ionizes is on the end. Now, with weak electrolytes, remember that we don't use a one-way arrow. We use the I can't make up my mind arrow, a back and forth arrow. So that's how you'll know it's a weak electrolyte, or how you'll indicate that it's a weak electrolyte. So your products would look like this. That would be AQ as well. So this is the same reaction, just written a different way. I want you to be familiar with seeing it both ways. You can also see this written, put in parentheses here, HC2H3O2. So that means the same thing. So carboxylic acids are weak electrolytes. They ionize partially. So at any given time you have more molecules than ions with weak electrolytes. Strong bases. Since they're strong bases, they are strong electrolytes. They ionize completely. The strong bases that you should know and memorize: sodium hydroxide, potassium hydroxide, lithium hydroxide, and calcium hydroxide. So calcium hydroxide is a strong base. You might think based off your solubility rules that it's not, but it is. Just accept that. Know that I've told you. Ionization reactions for your strong bases: one-way arrow, and all ions are formed. And finally, weak bases are weak electrolytes. They partially ionize. The weak bases that we'll see are amines, so anything containing a nitrogen. Now, either way, you can see it written with water above the arrow or water as a reactant. Amines are Bronsted-Lowry bases. You guys just learned this in the last lecture. I'll give you a refresher. Bronsted-Lowry bases are proton acceptors. So, amines will get their proton from water. So if you look at a change from left to right, NH3 is going to grab a proton from water, so it'll be NH4 plus, leaving OH minus. So that would be your ionization reaction for NH3 and water. And it's basically that way for all amines. They're just going to grab a proton from water and produce positively charged ammonium salt, or NH something plus, and then OH minus. And now you can see water written above the arrow or to the left of the arrow, but the same thing occurs in this reaction. So amines are greedy. It's the best way I like to explain this. Amines are mean and greedy. They want as many protons as they can get. The reason I go through and explain that amines are mean and greedy is that a lot of times students mistake amines for acids. This is what not to do. Don't do this. NH3 plus water. Because there are hydrogens on this NH3, students think that, oh, this is what will happen. You'll get NH2 and H3O plus because of these protons. That is not what happens. So whenever you see a nitrogen, think mean and greedy. It's going to grab a proton from wherever it can get it. If it's water, if it's HCl, it's mean and greedy. It wants protons. Okay, so on the next page I have reactions that I want you to complete. I also want you to specify whether it's a weak electrolyte or a strong electrolyte. So I want you to hit pause and complete these reactions. Okay, so the first one, HCl, it ionizes completely, so it is a strong electrolyte. H2SO4 is a strong acid, so it is very helpful to memorize these strong acids so you know what products you'll get. It's a strong acid, ionizes completely, strong electrolyte. Make sure it's balanced. HF is a weak electrolyte or weak acid because of the double-headed arrows. It's also not one of the 6 strong acids you memorize. So if it's not one of the 6, you can assume it's a weak acid. Sodium hydroxide is a base. It's a strong base, so it's a strong electrolyte. NH3, remember that's a mean and greedy amine. So it wants protons. It's not a strong electrolyte, though. It's a weak electrolyte, and you can tell based on the double-headed arrows. CH3 and H2, you guys know how to name this, right, from Unit 4. This is methylamine, or methanamine. It's also an amine, so it's going to be greedy and grab protons from water. So you'll get these products. It's a weak electrolyte. Acetic acid the structure wasn't provided, you can draw the structure this way, or you can draw a condensed structural formula like you did for Unit 4. Either way, products you get are acetate ion and hydrogen ion. It's a weak electrolyte. Now, remember way back when you're trying to learn these polyatomic ions, you're thinking, how am I supposed to remember acetate ion? This is acetate ion. It comes from acetic acid, so you can kind of see how the name is generated. Maybe that will make it easier for you to remember that pesky acetate ion. So, at this point, there is a lot that you can do for Lab 22, conductivity. There are a lot of reactions that you can complete that are within the experiment. On the back page, you can work on those reactions. It asks if there are strong electrolytes, weak electrolytes. Also asks for a lot of ionization reactions. Many of them, which are on this page of your notes. So, if you want to practice this, work on Lab 22. And I'll talk more about that lab when we actually get to the lab, but just you can practice the ionization reactions we just went over on that lab. So we're going to move on in Unit 5. We're kind of getting close to the end of Unit 5. We've been talking about acids and bases and electrolytes, strong electrolytes, non-electrolytes, all of that. It turns out that water itself ionizes to a small extent. So read this sentence and you think, water ionizes to a small extent. What is she talking about? Well, water, even if it's deionized water, will conduct a small amount of electricity. That's because it auto-ionizes. So, it's a weak electrolyte, since it ionizes to a small extent. Weak electrolyte. So that's why I use the double-headed arrows. It's going to break up into H plus and OH minus. So it will conduct a small amount of electricity. At 25 degrees Celsius in pure water, the concentration of hydrogen ion, or you can see this written as hydronium ion, it means the same thing, is 10 to the negative 7th molar. And the hydroxide ion concentration is 10 to the negative 7th molar. That makes it neutral because you have an equal concentration of hydroxide ion and hydronium ion. So hopefully the water you're drinking is neutral. Now, the ion product constant of water, Kw. Kw is defined as the product of the hydrogen ion concentration and the hydroxide ion concentration. So, ion product constant of water, H plus. So brackets mean concentration, denoted by brackets. Ion product constant of water is the product of the hydrogen ion concentration and the hydroxide ion concentration. Now, product, when you're talking about math, does that mean multiply or divide? It means multiply. So you're just going to be multiplying these two concentrations. You will always get the same Kw. It's a constant. It's always 10 to the negative 14th. So Kw is always constant. So the reason I'm talking about this is because knowing the ion product constant of water is very helpful in determining whether we have an acidic, basic, or neutral solution. So, if you look at this table, if you have an acidic solution, do you think you have more H plus or more hydroxide? You have more H plus. So your H plus concentration will be greater than your hydroxide ion concentration. So an example, If you have a concentration of 10 to the negative fifth of your hydrogen ion concentration, what would your hydroxide ion concentration be? We know enough information at this point to figure this out. Since we know Kw is always H plus times hydroxide, in this problem we're given 10 to the negative fifth for our hydrogen ion concentration. We know that Kw is always 10 to the negative 14th. Now we just have to solve for our hydroxide ion concentration. So if we, I'm going to write this up here, hydroxide ion concentration will be 10 to the negative 14th divided by 10 to the negative fifth. So we're dividing powers of 10. So to do this mathematically, you can get out your calculator and look for the exponent key, or you can do a shortcut. To divide powers of 10, you just subtract the exponent since they're the same base. So, to come up with a hydroxide ion concentration, we just need to say 10 to the minus 14th minus negative 5. So minus 14 plus 5 will give us 10 to the negative 9th. So our answer right here is 10 to the negative 9th. Or an easier way to do this is say the exponents of the hydrogen ion and the hydroxide ion must always add up to 10 to the negative 14th. So does negative 5 plus negative 9 add up to negative 14? Absolutely. Then you don't have to go through all this rigmarole of dividing and trying to remember the rules. So to multiply powers of 10, you just add the exponents. Okay. So in a basic solution, do you think the hydrogen ion concentration is higher or lower than the hydroxide ion concentration? Turns out that it's lower than the hydroxide ion concentration. So if you have a hydrogen ion concentration of 10 to the negative 11th, your hydroxide ion concentration will be 10 to the negative 3rd. And remember that we're dealing with negative exponents. So the larger the negative exponent, the larger the number. So it might seem at first glance that 10 to the negative 11th is actually higher than 10 to the negative 3rd. That's not the case because we're dealing with negative exponents. Now for a neutral solution, your hydrogen ion concentration is equal to your hydroxide ion concentration. So you know that 10 to the negative 7th is your hydrogen ion concentration. Your hydroxide ion concentration will also be the same. Now, let's talk about pH. You've probably heard of pH before. It's a very useful quantity. pH is the absolute value of the hydrogen ion exponent, the absolute value of the hydrogen ion exponent. So for example, if I have the hydrogen ion concentration as 10 to the negative 3rd, the pH is just the absolute value of that exponent. So the pH, or the power of the hydrogen ion concentration, that's what pH stands for, is 3. So an acidic solution has a pH of less than 7. An example of an acidic solution would be hydrogen ion concentration of 10 to the negative 5th, molar hydroxide ion concentration. You guys can tell me this. The hydrogen ion concentration is 10 to the negative 5th, and the hydroxide ion concentration, remember that those two exponents have to add up to negative 14. It's going to be 10 to the negative 9th molar. The pH will be 5. A neutral solution will have a pH of 7. And you know, when we say neutral in lab, it doesn't have to be spot on neutral. About 7 is ideal. So from a pH of 6.5 to 7.5 would be neutral. You kind of think of it when we're trying to neutralize our waste. We're not trying to get it exactly at 7.00. We're trying to get it into a range of neutrals. So it's not too acidic and not too basic. When you have a neutral solution that is spot on neutral, your hydrogen ion concentration is 10 to the negative 7, hydroxide ion concentration is 10 to the negative 7, and your pH is 7. So water is roughly neutral. When you take the pH of water in lab, you might find it's 6.7. Call it neutral. It might be 7.2. Call it neutral. So your blood is considered neutral, and it has a pH of about 7.35. So just to give you an idea. A basic solution has a pH of greater than 7. The hydrogen ion concentration is 10 to the negative 11. If I gave you that, then you can tell me that the hydroxide ion concentration is 10 to the negative 3, and the pH would be 11. Alright, so I have a question for you. Which solution has a higher hydrogen ion concentration? One with a pH of 5 or one with a pH of 9? So, higher hydrogen ion concentration. So let's look at the pHs. pH of 5, pH of 9. The hydrogen ion concentration, in the case of a pH of 5, would be 10 to the negative 5th. The hydrogen ion concentration in the pH of 9 would be 10 to the negative 9th. So which one has the higher hydrogen ion concentration? It's tricky, because you might think it's 10 to the negative 9th, but that's actually the smaller number. So this one actually has the higher hydrogen ion concentration. Let's look at the hydroxide ion concentrations now. That's going to be 10 to the negative. We need to add up to negative 14, so negative 5 plus negative 9 would give you 10 to the negative 14th. Do the same thing down here. 10 to the negative 9 plus 10 to the negative 5th. So the higher hydroxide ion concentration is the solution that has a pH of 9. So, what do you guys think about soda? Do you think it's acidic or basic? Turns out that soda is acidic. It has a pH of about 3. So a lot of students think soda is really not that acidic. If you look at water, water has a pH of about 7. So I think, well, soda's probably, since water has a pH of about 7, that just means that soda is 7 minus 3. Soda is 4 times as acidic as water. So it's really not that bad for me. Wrong. It's not 4 times as acidic as water. Since each number on the pH scale is actually a power of 10, it's a lot more acidic. So not 4 times as acidic. Try 10 to the 4th times as acidic as water. So that means soda is 10,000 times more acidic than water. So that's why if you drink a few 2 liters of soda a day, you will take the enamel off your teeth because it's so acidic. And you know, growing up, my dad was a dentist. Still is in practice. And he was so against sugar. So sugar was the enemy. Don't eat candy that's bad for your teeth. And of course, I have a major sweet tooth. But, you know, if we ever had sodas in the house, they had to be diet sodas, right? Diet Coke. And, you know, so he would always, if you're going to drink soda, drink Diet Coke. Well, it turns out all this research on these sodas doesn't really matter whether it's diet or regular, because they're both so acidic. They're both equally bad for your teeth. You know, like everything, enjoy it in moderation. Just a little bit doesn't hurt, but when you have massive amounts of soda, whether it be diet soda or regular soda, the enamel will come off your teeth. So hopefully I haven't ruined soda for too many of you, but at any rate, I think it's interesting to recognize how much more acidic soda is than water. So we'll stop here for this lecture. For your acids and bases lab, lab 23, you can actually work on the pre-lab for that one. You can fill that in. It's just a table of hydronium, hydroxide, pH, and acidic, basic, or neutral table. So that you can go ahead and fill out. Otherwise, I want you to do your homework problems that pertain to the sections we covered. I'll have one more lecture on Unit 5, and we have covered a lot of material in Unit 5. I think part of the issue is it's kind of a review of previous units, but it's a broad unit. So go back and review some of Unit 5. Even though we're getting to the end, go back and try and see, oh, those solubility rules, oh, yeah. So work on that. Until next time.